The effectiveness of a grounding electrode system can be influenced by its proximity to neighboring systems. When multiple grounding electrodes are positioned close together, they can interact, potentially affecting overall grounding performance. This interaction arises because current flowing through one electrode can induce a voltage potential in nearby electrodes. Given the close vertical spacing of approximately 6 feet between the grounding electrode systems, there exists a possibility of interaction. Such interaction can lead to a reduction in the overall grounding effectiveness of both systems. Several approaches can be considered to mitigate this potential issue. Firstly, additional grounding electrodes can be installed to supplement the existing system. By increasing the number of electrodes, the current flow is distributed more evenly, reducing the potential for interaction between individual electrodes. Secondly, alternative types of grounding electrodes may be considered. A buried ground ring, which encircles the structure, provides a more extensive contact area with the earth, potentially improving grounding performance and reducing susceptibility to interference from nearby systems. Thirdly, a concrete encased electrode, also known as a U for ground, involves encasing a grounding conductor within concrete that is in direct contact with the earth. This method provides a large contact area and can be particularly effective in enhancing grounding performance. The National Electrical Code, or NEC, provides guidelines and requirements for grounding electrode systems. It's crucial to adhere to these standards to ensure safety and effectiveness. The NEC specifies requirements for the size and type of grounding conductors, the number and spacing of grounding electrodes, and the bonding of metallic components within the electrical system. Ultimately, the most reliable method for determining the effectiveness of a grounding electrode system is to have it tested by a qualified electrician. The electrician can perform measurements to assess the resistance between the electrodes and the surrounding earth, comparing these measurements to the requirements outlined in the National Electrical Code. Low resistance to ground is essential for proper grounding, as it provides a path for fault current to flow back to the source, facilitating the operation of overcurrent protection devices like circuit breakers and fuses. Higher resistance to ground can impede the flow of fault current, increasing the risk of electrical shock and equipment damage. The electrician can use specialized equipment such as a ground resistance tester to measure the grounding impedance of the system. This test involves injecting a current into the grounding electrode and measuring the voltage drop across a known resistance. The measured impedance can then be compared to acceptable limits specified in the NEC. The NEC provides specific requirements for grounding electrode systems based on the size and type of electrical service. For instance, the NEC specifies the minimum size of grounding electrode conductors, which are the conductors that connect the grounding electrode to the electrical system. The size of the grounding electrode conductor is typically determined by the size of the service entrance conductors. The NEC also specifies the types of grounding electrodes that are permitted, which include metal underground water pipes, metal frames of buildings, concrete encased electrodes, ground rings, and ground rods. The NEC requires that grounding electrodes be installed in contact with the earth and that they be free from non-conductive coatings or corrosion. The NEC also addresses the bonding of metallic components within the electrical system, such as metal conduits, metal enclosures, and metal piping systems. Bonding ensures that all metallic components are at the same electrical potential, reducing the risk of electrical shock. The NEC specifies the methods for bonding metallic components, which include using bonding jumpers, bonding bushings, and other approved methods. In addition to the NEC, local codes and regulations may also apply to grounding electrode systems. It's essential to consult with local authorities to ensure compliance with all applicable requirements. Regular inspection and maintenance of grounding electrode systems are crucial for ensuring their continued effectiveness. Grounding electrodes can corrode over time, reducing their ability to provide a low-resistance path to ground. Inspection should include visual examination of the electrodes and conductors for signs of corrosion or damage. Resistance measurements should also be taken periodically to verify that the system is still meeting the requirements of the NEC. If corrosion or damage is detected, the affected component should be repaired or replaced promptly. Maintaining a low resistance ground is essential for protecting people and equipment from electrical hazards. A properly installed and maintained grounding electrode system can help to ensure the safety and reliability of the electrical system. Factors affecting grounding electrode system performance include soil resistivity, electrode material, electrode size and depth, and the presence of underground utilities. Soil resistivity is a measure of how well the soil conducts electricity. Low soil resistivity is desirable for effective grounding. Soil resistivity varies depending on the type of soil, moisture content, and temperature. Electrode material also affects grounding performance. Copper and copper-clad steel are commonly used for grounding electrodes because they are good conductors of electricity and resist corrosion. Electrode size and depth also affect grounding performance. Larger electrodes and deeper installations generally provide lower resistance to ground. The presence of underground utilities can also affect grounding performance. Underground utilities, such as water pipes and gas lines, can provide alternative paths for fault current to flow, potentially affecting the effectiveness of the grounding electrode system. It's essential to consider the location of underground utilities when designing and installing a grounding electrode system. Grounding electrode systems are designed to provide a low impedance path for fault current to return to the source. This helps to ensure that overcurrent protection devices, such as circuit breakers and fuses, operate quickly to clear faults and prevent electrical hazards. A properly designed and installed grounding electrode system is an essential component of a safe and reliable electrical system. In summary, firstly, the proximity of grounding electrodes can affect their performance due to current interaction. Secondly, mitigation strategies include additional electrodes, ground rings, and concrete encased electrodes. Thirdly, professional testing is crucial to verify NEC compliance and low resistance to ground. And fourthly, proper maintenance and consideration of factors like soil resistivity are essential for long-term effectiveness.